Hello everyone. Today I will give the presentation on our work, VELTAIR, towards high-performance multi-tenant deep learning services via adaptive compilation and scheduling. I'm Zihan from Shanghai Jiao University, and this work is sponsored by Shanghai Qizhi Institute. Here's the outline of the presentation. And first, I will introduce the background and related work. It's universally acknowledged that deep learning applications are evolving fast and are becoming more and more complex. For example, in cloud services and autopiloting, we need to provide services to several deep learning models simultaneously. However, currently, the computation power of hardware also increased significantly as shown in the middle figure. And this situation resulted in a problem that the performance of a single hardware is far beyond the requirement of a single inference task of deep learning model. As shown in the rightmost figure, the QoS requirement of ResNet 50 in MLPerf is 15 milliseconds, while the whole CPU can only use 6 milliseconds to finish the job. Under these circumstances, we need multi-tenant. In another word, we need to collocate multiple tasks or queries onto one hardware. After understanding the necessity of multi-tenant, I will introduce some current solutions. We can divide current solutions into hardware and software solutions. The hardware solutions mainly bypass the complex resources management of collocating tasks by temporal sharing or physical isolation, like AIMT for temporal sharing and NVIDIA MIG for resources isolation. For software solutions, there are some task collocating solutions for traditional workloads, including parties. For deep learning tasks, Dart proposed a cluster-scale scheduling strategy, while today our work mainly focuses on a CPU-scale strategy. Of course, we have some simple, straightforward solutions. On CPUs, we can use NPI to serve multiple tasks and use CPU affinity and tools including REST control, Intel CAT, to limit or manage resources usage. While on GPUs, we have multi-process service, persistence thread blocks. These techniques support simply dumping multiple tasks onto a single hardware. The right figure shows an example code of doing so on CPU and GPU. But how about performance? It's not good. To illustrate the limitation of straightforward solution, we set up a simple experiment to evaluate. First, we observe a significant latency increase when collocating multiple tasks together. For GoogleNet, we have a maximum of 80% increase in latency if we collocate 4 identical instances on a CPU. By querying the performance counter via PuPy, we found that the LLC miss rate increased dramatically. Second, we try both fine and coarse-grained scheduling. The performance are both far less than the theoretical performance calculated by the G-flops of the CPU. So, we aim to optimize the interference and scheduling granularity in multi-tenant scenarios. We further analyze the bottleneck of the existing solutions. For interference, we sample multiple code implementations from the TVM auto-scheduler, aka Answer, and profile the performance under isolated execution and collocating. We take two representative implementations as an example. The red one performs well and the yellow one performs poorly under isolated execution, while the situation is totally contrasted under collocation. The red one performs poorly while the yellow one performs well when 4 tasks are collocated. For scheduling granularity, we found that though finer grain leads to a higher CPU efficiency, since we can assign different CPU cores to operators with different computation features, fluctuated CPU usage will lead to frequent conflict, where conflict means the spare slot of the CPU is not enough for an operator. While if we use coarser grain to reduce the fluctuation, the CPU efficiency will be significantly damaged since operators with different computation features now use identical CPU cores, which leads to overkill for some operators with low scalability. That means high efficiency and low conflict cannot be achieved simultaneously if we only use static granularity. And before we derive the solution, we first simply go through the optimization of computer programs. The optimization is a trade-off between parallelism, locality, and computation efficiency, while in this work, we only consider 2 former factors. Now, given a simple program and our assumption that LLC miss has 200 cycle penalty and the ALU costs 1 cycle to calculate plus, the left implementation uses only 1 CPU core, while it will occupy the LLC for 60% of its latency. While with the identical latency, the right implementation implementations with loop tiling will occupy the LLC for only 20% of its latency, though it will cost 3 CPU cores, which means we trade low shared resources usage with high exclusive resources usage. Note that the locality decreased from 1 LLC miss to 6 LLC misses, while parallelism increased from 1 core to 3 cores. Now we will introduce the main methodology of this work. According to previous findings, we systematically conclude the insights of the design. First, for interference, the operators prefer low locality but high parallelism implementations under heavy interference, since it has lower shared resources contention, while the operators prefer high locality but low parallelism implementations under light interference, since it uses fewer CPU cores. With the red arrow, operators' preferences shift from bottom right to top left, from light interference to heavy interference. Second, for scheduling granularity, we found that finer granularity is better under low system load, since the conflict possibility is low. It can achieve better CPU efficiency, while coarser granularity is better under heavy system load, since the conflict possibility is high, with more tasks collocated on the hardware. And given these 2 insights, we designed 2 main modules. We first extend the existing TVM autoscheduler, aka Answer, but in contrast to Answer selecting only 1 best implementation under isolated execution, our work will first choose all implementations capable for finishing the job in time, and extract the non-dominant implementations, aka Pareto frontier, according to both locality and parallelism by inspecting the blocking size and parallel pragma of generated code. Then we will select 5 implementations with different locality and parallelism on the Pareto frontier to handle different interference. We then implement a dynamic granularity scheduling algorithm. We split the model into several layer blocks. Operators inside the layer blocks are assigned identical CPU cores, while may be different from other layer blocks. We split the model from the operators that are likely to cause conflict. We define an operator to be likely to cause conflict if the operator uses more CPU than the current average spare slot of the whole CPU, where the average spare slot is the whole CPU cores minus average CPU cores of all active tasks. Finally, we put things together and implement VELTAIR on CPU by MPICH. At compile time, we will prepare multiple implementations to handle runtime interference. And at runtime, we will schedule the model at dynamic granularity with layer block pattern. Then, we will introduce our evaluation process. We evaluate our system with MLPerf server suite as shown in the table. We use 7 different deep learning models ranging from vision to neural machine translation. We mainly evaluate the service providing ability and the inference latency of the new system. The workload generates the query following the Poisson distribution, where the lambda indicates the QPS of the workload. We evaluate our system on a high-end CPU platform with 64 physical cores and 256 gigabytes main memory. To get a stable result, we disable simultaneous multi-threading and DVFS of the CPU. The result shows that we have 71%, 62%, and 45% improvement in service providing ability in light, medium, and heavy workloads, respectively. The service providing ability is the maximal QPS with 99% of the queries being satisfied. For inference latency, the system decreased the inference latency under multi-tenant scenarios by 50% on average. Note that the multi-version compilation will result in increased CPU cores usage, which may cause more frequent conflict, while dynamic granularity can shrink the negative effect. Thus, we get a 1 + 1 > 2 result. Then we discuss our design space. In this work, we select 5 implementations for every operators, considering the balance between improvement and overhead. The improvement increased slightly using more than 5 implementations, according to the left figure. According to the right pie chart, over half of the operators will use more than 3 different versions to handle interference. When it comes to the overhead, we have overall 13 megabytes runtime storage overhead for generated binary code, which is small comparing to the weight and feature map storage in deep learning workloads. Now we draw the conclusion. In this work, we first systematically analyzed the optimization opportunities of multi-tenant deep learning workload. Then, we propose multi-version compilation and dynamic granularity scheduling to hit the balance between 2 trade-offs. The first is locality and parallelism at compile time, and the second is efficiency and conflict at runtime scheduling. On the standard MLPerf suite, we increase the service providing capability by 60% on average, and we decrease the inference latency of 7 different deep learning model by 15% on average. We are now extending our work to more hardware, including GPUs and ASICs. Thanks for listening. Any questions?